So we're ready to start the second session of the symposium. We heard about some key devices in the first part. Now we move to more systems with this following talk that will be given by Neil Bergano. Neil Bergano is the Vice President of R&D and Chief Technical Officer of TE Subsea Communications. He's widely recognized for his research on long-haul optical fiber systems, including the use of wavelength division multiplexing in optical fiber-based systems. Neil is a fellow of the IEEE, the OSA, AT&T, and TE Connectivity. He's a recipient of the year 2013 TE Connectivity Lifetime Achievement Award, and he received the 2002 John Tyndall Award for outstanding technical contributions and technical leadership in the advancement of global undersea fiber optic communication systems. Neil.
Thank you. Thank you for that kind introduction. That's fine. Thank you for that introduction, and good morning, or good afternoon, everyone. It is my pleasure to participate in this symposium that is just conveniently enabled, titled for me, Enabling the Global Internet. So this afternoon, I'll be talking about the capabilities of the undersea communications industry. And of course, I'll touch on the history and technology behind that. And while I'm doing that, I'll try to touch on some of the things that you might not know about undersea cables. And then we'll do a little speculation as we go forward of where we might be going. But I'd like to start the talk with a story. And the story goes something like this. You're on vacation and you see something interesting. So what do? You take out your smartphone and you take a photograph. And if you like that photograph, you probably send it to somebody. So here's a question. These days, do you ever think about where in the world that person is? Or do you ever care where that person is? No, you send it, and the photograph arrives like magic. And it reminds me of a famous quote from my favorite science fiction writer, Arthur Clarke, who said, "Any sufficiently advanced technology is indistinguishable from magic." And I would imagine for the common user of the mobile network, it is magic. But we're a group of optical communication specialists, so I hope you can understand and appreciate that obvious use of undersea cable systems. There are more ways that we use undersea cable systems that are not as obvious. How about just a regular old internet search? Here it's not as obvious, but consider all of the data centers around the world from all the big content providers. Connecting these things takes lots of bandwidth. And all of this is provided, well, the bandwidth between these data centers are provided by undersea cables. So nowadays, information moves around the world almost seamlessly. And the world is connected with a web of undersea cables. And that means anybody that surfs the web, calls overseas, sends texts or tweets to anybody overseas, are using undersea cables. So information moves around the world almost seamlessly. But it wasn't always that way. If you think about it, a long time ago, information went no faster than the person carrying it. And that was pretty much true until the commercialization of the electric telegraph system back in the early 1800s. And telegraph was widely successful, and those terrestrial networks fanned out across the continents and stopped at the ocean's edge. So it was only natural that people would want that connectivity from continent to continent. Well, as Emmanuel said earlier, that first system was installed in 1858. You know that saying about leading and bleeding edge of technology? Well, this was definitely the bleeding edge of technology. The system was rushed. The technology wasn't well understood. The manufacturing started way too early, and the system only worked for 1 month. Well, many prominent engineers and scientists worked on the review panel, and undaunted, people tried again, and 10 years later, the first successful cable system went into operation in 1866, and as I said, that was successful, and international telecommunications was never the same. It took about 90 years from the time of that first successful transatlantic telegraph to the time of the first successful undersea telephone cable across the Atlantic. That was installed in the 1950s and had a handful of analog channels. That first system was TAT-1, Transatlantic Telephone Cable number 1, installed in 1956, and that was installed with 32 4 kilohertz analog carriers. Now, over the next couple of minutes, I'm going to walk around this chart, and this chart shows the growth of the capacity of undersea cables over the last 60 years. And what is truly amazing is, over those 60 years, the capacity has increased by 7 orders of magnitude. Now, first, those analog cable systems, they were installed with coaxial cables with RF amplifiers. The first system that was installed in the 1950s used vacuum tube amplifiers. And again, it's installed with just a handful of channels. Well, that technology eventually progressed to the point where the capacity reached 4,200 analog circuits, again, using frequency division multiplexed, using electrical amplifiers. And does that sound a little bit like WDM? Here's an interesting twist of fate. In those systems, the cable was completely linear, but the nonlinearity everybody worried about was the electrical amplifiers. So in the 1980s, work started in earnest on developing digital optical carriers for transoceanic telecommunications. And the first transatlantic system was put in 1988, which was TAT-8. And this was an amazing amount of work, and it revolutionized international telecommunications. But looking at my chart here, by historical standards, the improvement in transmission capability really wasn't that great. And that brings me to what I've labeled the capacity dilemma that people had back then. And the capacity dilemma went something like, optical fibers had a huge amount of intrinsic capacity, but fiber optic systems using electro-optic regenerators did not. Now, I labeled this the 90s capacity dilemma, but looking around the room at all the faces I know, we could have easily labeled this the 80s or the 70s capacity dilemma, because this was well understood early on that optical fibers had huge bandwidth. And of course, as Emmanuel said, optical amplifiers removed that bottleneck, and then wavelength division multiplexing was possible, and the first systems realized that channels interact. Dispersion management techniques were invented that alleviated that problem, and Annie's going to be talking a lot about that next. New transmission formats were invented to let the bit rates per channel go up, and strong forward error correction, and most recently, coherent communications. You know, to where we are at the point today, and you think about a typical new undersea cable, think about 10 terabits per second per fiber pair. Just rough round numbers, 100 channels, each operating at 100 gigabits per second. And so these days, using optical amplifiers, first with direct detection and then with coherent detection, several more orders of magnitude of growth was possible. So now I'm going to talk a little bit about the capabilities of the undersea cable industry and try to compare and contrast that with terrestrial systems. And probably the most obvious difference is the unregenerated transmission distances in undersea cable. And we're talking about distances of about 5,000 to 7,000 kilometers to go across the Atlantic, and anywhere from 9,000 to up to 12,000 kilometers to go across the Pacific. So let's look at a cartoon of an undersea cable system. And as I said, the distances are long, so there's obviously lots of cable. We use the gain in an erbium-doped fiber amplifier to compensate the loss in the cable. And we put these erbium-doped fiber amplifiers into repeaters. And because I'm an undersea cable person, you might hear me interchangeably using amplifiers and repeaters. Somehow the term repeater has survived since the telegraph days and 200 years of technology paradigm shifts. The repeaters that we use come in 2 flavors. There's two cable repeaters and then 3 cable repeaters for branching to allow for trunch and branch optical networks. The cables that we use look very different from terrestrial cables. The single mode fibers sit in a loose tube, and a loose tube is just a perfect environment for high performance fibers. The loose tube is surrounded by high strength steel wires. That's surrounded by a copper jacket, and the whole thing is embedded in a polyethylene insulator. And that forms a nice pressure vessel. So you might be surprised to know that those fibers, even at the bottom of the ocean, are sitting at atmospheric pressure. Now, typically people think of an undersea cable, they think of something big, but to get a better sense of scale, think about a garden hose. The basic undersea cable is only 17 millimeters or 3/4 of an inch in diameter. And that's not to say it isn't strong. The breaking strength of that 17 millimeter cable is about 18,000 pounds. So that could support the weight of about 5 Toyota Camrys. We start off with the basic cable, and then onto that we add different layers of protection. And as we go into different parts of the ocean require different levels of protection. As it turns out, the deepest part of the ocean is the safest part of the ocean and typically gets the smallest cable. And then as we go up the shoreline or up the continental shelf, we'll put different layers of protection and even bury the cable under the sea bottom. The optical amplifiers that we use look very different from terrestrial amplifiers. Again, we call these repeaters. These are high pressure vessels. We make ours out of beryllium copper, which is a material that doesn't corrode in salt water. We can deploy these up to 8,000 meters deep. Typically, in an undersea cable, there's many fewer fiber pairs than in a terrestrial system. Here we're talking about anywhere from 1 to 8 fiber pairs typically are installed. Since we can concatenate many more amplifiers in series than terrestrial systems, we need to do the gain equalization much more exacting. So you think about that trans-Pacific system might have more than 100 amplifiers in series. So we typically gain equalize those to the milli-dBs, even across the entire C-band. And of course, we put undersea systems in, we expect them to live for 25 years, so these are very high reliability designs. Now, erbium-doped amplifiers require electrical power. So how is that done? If you looked carefully at the photograph of the undersea cable, you might have noticed there's only one conductor. And the way we power a system is by sending a DC current through the single conductor and using the ocean as a return path. We do that by putting sea-ground electrodes at either sides of the cable's end. If we were to bias our 10,000 kilometer cable at 750 milliamps, it takes about 12,000 volts to bias that cable. Now, in practice, the way we would do that is put 2 power systems, one at each end, and run them at plus and minus 6,000 volts. And this has some obvious advantages and not so obvious advantages. One of the obvious advantages, in the case of one of the power supplies fails, you can power the whole thing from one side. One of the less obvious advantages is if we should happen to have a shunt fault, and that's a fault where the cable gets nicked and can touch the seawater and shunts to the ocean ground, we can take those the voltages of the 2 ends and unbalance them and put that shunt fault at virtual ground so the cable doesn't get eaten away. So you have enough time to sail the cable ship there and do a repair. At the bottom left-hand side of the slide, I have a little accounting of the voltages involved, and you might see something strange labeled 1,000 volts for earth potential. So here's a question. Is earth potential the same in Tokyo as it is in LA? Something you never even think about until you run a wire between the two cities. And of course, that's exactly what we do in undersea cables. And as it turns out, the ocean, the ground potential moves around by tens of volts in any typical day until the time where you get solar storms. And during solar storms, that can go up by several hundred volts, depending on the cables going east or west, north or south, and what part of the world it is. So we have to allow for some margin on the power feed equipment to allow for changes in earth ground potential. Now, I said I was going to talk about the differences with terrestrial systems, but one of the similarities is that we use optical add-drop multiplexing trunk and branch networks all the time in undersea cables, and that makes sense because we're talking about capacities that are rather large for each fiber pair, on the order of 10 terabits per second for fiber pair. And it makes the design a bit more efficient if you can design it to share capacity among many users. So in my little cartoon of an undersea cable, I pointed out some of the installation tools that we use. And in the next couple of slides, I want to give you a sense of scale for the equipment that we use in undersea cables. As I said before, when we go from the deep water into the more shallow water, we put different layers of protection on, and then we can bury the cable under the bottom using a sea plow. Now, when I started with the company about 35 years ago, and I heard we had a sea plow, I was envisioning something like, a lawnmower. And again, just to give you a sense of scale, this is our Sea Stallion 3 sea plow, to give you a sense of how big it is. And we use big things in undersea cables. This can trench and bury a cable up to 3 meters below the bottom of the ocean seabed, down to 2,000 meters deep. Actually, we have specialty plows that we can use in really muddy environments that can go all the way to 10 meters deep. Speaking of large tools, here's a photograph of one of our cable ships. This is a Reliance class. This happens to be the cable ship Durable. We have 8 cable ships in our fleet. And if we take a look inside of the ship and peel back the layer of the onion here, we can see some of the interesting parts of the ship. First of all, it's a hybrid electric vehicle. The multiple diesel engines on this ship just run electric generators, and the whole propulsion system is electric. On the bottom left, I've underlined something called dynamic positioning technology. So this ship out in the middle of the ocean, in a 24-mile-an-hour wind, with waves hitting it, can hold station to 2 to 3 meters over a 24-hour period. And that's fairly remarkable for a ship that's almost 500 feet in length. Those 3 large cable tanks that you see can hold 8,400 tons of cable. Now that's enough cable to go from New York to London in one run. And speaking of those cable tanks, these cutaway diagrams just don't do it justice. So, if we look inside of one of these cable tanks, you can really get a sense of scale for how much cable we're talking about is needed to go across the world's oceans. If you think about it, when you're manufacturing cable, you want the cable factory to be near a deep water port so that you don't have to transport that cable over land. And this happens to be our cable factory in Newington, New Hampshire. Maybe even for the US folks that live on the East Coast, you have to know your geography well to know there's a deep water port in New Hampshire. Now, when we typically think of undersea cables, we think of the telecommunications industry, but undersea cables are important for the oil and gas and scientific networks. This is a photograph of one of our cable ships that is just 50 meters off of an oil and gas platform. And here you can get a sense of why that dynamic positioning is so important, because the oil and gas people are very safety conscious. This shows the Gulf of Mexico fiber network that we installed in 2007. This is a 1,200 kilometer specialty purposely built system just for the oil and gas networks. This originally hooked up 7 oil and gas platforms back in 2007. We've subsequently come around and upgraded this and hooked up an additional 6 platforms. And you might wonder how we keep adding platforms to this network. And this slide just shows some of the specialty purpose-built equipment that we've designed and manufactured for the oil and gas networks and systems. So for instance, if we have a trunk cable, and then we have a branch cable that we hook up, we pre-install fiber distribution canisters. These are undersea wet mateable single mode connectors that we can come in with a ROV, or remotely operated vehicle, and hook up more platforms too. And we have different types of cables. That cable in yellow is going up and down in the water column, and the design of that cable is very different than a cable that lays on the bottom of the ocean. These cable systems can also be very useful for the scientific community, where the scientific community typically puts up observatories remotely located on the bottom of the ocean. And there, not only are they interested in telecommunications, just regular old data capacity, but they're interested in getting electrical power to the undersea node. And here, if the power requirements are modest, we can just simply power it off of that center conductor in the cable that we were talking about before. If the power requirements are more than just a little bit, well, we've designed dual conductor cables. So for instance, on the inner conductor, we can power the repeaters, and on the outer conductor, we can power the undersea node. So just to sum up this part of the talk, and thinking about the capabilities of the undersea cable industry, think of systems these days that are 10 terabits per fiber pair. Nice round numbers again. Think of 100 channels, each channel operating up to 100 gigabits per second. We put up to 8 fiber pairs on a cable, and these systems are useful for both the scientific and oil and gas communities. So now I'd like to think about transmission capacity, where we are now, how we got there, and where we might be going in the future. So I'm going to start with this chart. And this chart shows the last 25 years of laboratory experiments in terms of how many bits per second per mode on a single fiber as a function of year. And I'd like to make a couple of observations and walk around this chart. And first of all, before the erbium fiber days, people were working with coherent receivers. And if you were to take the post-deadline session from Ecoc and take a look from the 1980s, you would see lots of papers on coherent communication. And they were thought to be the technology of the future. Then amplifiers came along, and people started doing the first WDM experiments. They were done with just a handful of channels operating at 2.5 gigabits. And again, these are all transoceanic length experiments. And the attitude back then was that EDFA's systems have infinite bandwidth. Well, it took about 10 years to completely fill that bandwidth. First in the C band, and then in the C plus L bands. And at that point, people realized, I hit the wrong button. People realized that systems don't have infinite bandwidth. They only have 5 to 10 terahertz. And the other interesting thing is that when people started playing with optical amplifiers and WDM, people considered using coherent detectors, but they realized that the nonlinear index in the fiber would prevent phase modulated signals. And actually, this was correct in the paradigm back then with dispersion management. Maybe call it a failure of imagination, just to realize that someday there'd be enough real-time computing power in an ASIC that you could compensate all the dispersion just in electronics. But that, of course, is what's being done today. And coherent communications have increased the capacity by another order of magnitude over and above the best direct detection systems. To the point now where if we look at the last few years, the capacity has been growing at about 30% per year. And again, that was after the bandwidth was completely filled. So all of those increases are characterized by increases in spectral efficiency. So that's a doubling of about every 9 years. And of course, it leads us to the question of, well, where are we going next and what's possible? So again, the first coherent systems allowed for a 10x improvement in transmission capacity. Well, as we all know, capacity is still important. Capacity demands keep growing. We want cost per bits to keep going down. And if we just think of this as an engineering challenge, we could probably see our way to the next anywhere from 4 to 8x in transmission capacity just by doing some good engineering or maybe great engineering. And you could think of ways where you can come up with a couple of factors of 2. For instance, right now, all of our systems use the C band. We can think about adding the L band to get twice the amount of optical bandwidth. Typical systems today use 200% spectral efficiency. And we can think of going up to 3 or 4 or 500% spectral efficiency. And that's real system specific, whether the systems are ultra long or just kind of regional in length. And combinations of fibers improvements, more efficient modulation formats, stronger FECs, and maybe we'll get another factor of 2 or so. So, real soft numbers anywhere from, 3 to 6 to 8x more just by doing great engineering. Now, of course, what we understand nowadays with the capacity limits, and we're talking about how much capacity we can get in a single mode, we have to deal with the nonlinear Shannon limit. But of course, people look at this sometimes in the wrong way because they think, well, there's just simply nowhere else to go. But of course, what we realize is that system capacity is going to scale with the bandwidth per mode the amount of modes per core, the amount of cores per fiber, the amount of fibers per cable. And so you can see that we still have orders of magnitude of runway out in front of us. And this is probably obvious if you look at the post-deadline session that's going to happen tomorrow, and if you look at some of those petabit papers, is that we might be running out of capacity in a single mode, but there's plenty of runway out there for the capacity in the cable. So I'd just like to finish up with another story, and just tell you something that happened earlier in the year. And one of my colleagues that started around the same time I did, and we were having a little celebration for his 35th anniversary. And because now I'm the CTO of the company, they looked at me and I had to say some words, and of course I had no words of wisdom, so I had to make up something on the spot there. And so I congratulated him from service, and I happened to find in the audience this one person that started that week, and I looked at him and I said, Luis, in the year 2050, at your 35th anniversary, and I think that just stuck in my throat, the 2050. And so I went back to my office and I was just kind of doodling, and I was wondering what could an off-the-shelf telecommunications system look like in 35 years? And probably given that my day job is optical communications and one of my hobbies is digital photography, I was thinking of, maybe we'll have multiple cores with multiple modes, and we'll have a single digital image processor, that'll have plenty of coherent pixels with lots of bandwidth, and a huge parallel ASIC sitting behind it. And when you think about it today, your off-the-shelf digital camera has 20 pixels, and there's a rough or a coarse WDM demultiplexer on them, the red, green, and blue pixels. So, is it crazy? Which reminds me of another famous quote from Arthur Clarke, who said, "New ideas pass through three periods. First is it can't be done, and second is, well, it can probably be done, but it's not worth doing. And then third is, well, I knew it could be done all along." So anyway, what I tried to give everybody today is just a sense of the capabilities of the undersea telecommunication systems, where they're used, not just in transmission systems, but oil and gas and scientific networks, and tried to give you just the ramblings of a technologist that's been around for 35 years or so. Thank you so much for the invitation. I really enjoyed it, and thank you for your kind attention.